This is Manchen Wang, and here is my lab report for Lab 2 of Physics. I'll have my lab report into the following parts: introduction, experiment and data collection, computational model, discussion, and conclusion. Here is the introduction of the experiment. So the purpose of the experiment is to observe and measure the motion and velocity of a falling object from rest, and it also uses Newton's second law to predict and calculate the velocity and position according to time and net force. The assumption of the experiment is that the object's falling motion will only be influenced by the force of gravity. However, the result of the experiment is that the object's falling motion will be influenced by both the gravitational force and the drag force from the air resistance. Here are the fundamental principles behind the experiment. The first principle is the Newton's second law, which states that net force on an object is equals to the mass times acceleration of the object. And using this function here, we produce the position update formula. In the experiment, we'll use the Newton's second law to first calculate the acceleration using the net force, and then use the acceleration to calculate the position and velocity of the ball. Here is the experiment video we created for the experiment, and we dropped the ball from rest in the video and used the tracker to analyze the whole video. The system here is the ball, and the surrounding is the rest of the environment. Here is the page 1 of the computational models I created for the experiment. To make sure that it represents more of the experiment video, I made delta t here into 0.033, which is the same as the time interval I used to analyze the video in tracker. Here are the separated code I constructed for the two computational models. The first model is the ball pulled only by gravity, and so here the drag force equals to 0, and the net force on the ball is only negative ball's mass times little g, which is set to 9.8 in the previous page. And here I use the position and velocity update formula to calculate the velocity and position of the ball, and the computer will use these formula to do iteration on the data and finally come up with a more precise result of the ball's position and velocity. And in this model here, the one with both gravity and drag force pulling on the ball, I set b equals to the square of the ball speed on the y direction. So, and here I added the drag force onto the net force field formula and did not change the velocity and position update formula. In both models, I set t smaller than 0.6 to make sure that it is the same with the video I recorded. Here is the overall data collection. And here is the graph I plotted using Excel. And you can see, as you can see here, the graph that the computational model with both drag force and gravity acting on it is exactly the same with the actual experiment I did, while the computational model with only gravity pulling on it falls quicker than the other two models. Here's the discussion of the experiment. So for the what does it mean question, so none of my experiment or model here actually reached the terminal velocity, but if I give them more time, the computational model with both drag force and gravitational force and my experiment model will reach terminal velocity, since they both have air resistance pulling against the gravitational force. And for the what if question, the terminal velocity of both objects will not change because at the time, the only thing that will influence the terminal velocity is the air resistance, and the gravitational force pulling on it. Both of them are only relevant to the character of the object itself, and its irrelevance was the initial velocity. Here is the conclusion of the experiment. The object's falling motion will be influenced by both gravitational force and air resistance, because the experiment dataset represents more of the computational model with both drag force and gravitational force.